So certainly we will use Q equal MC delta T, and here N is rho times V. So delta T, we don't need to convert to Kelvin. It's just the difference here, 165, which is 35. So it is 42 kg, okay? And if we go to the graph, we can find that this 42 is each very small square is equal to 2. So 42 is here, just one very small square above 40, and it makes the graph here at almost 270. So this takes 270 seconds. Again, the difference is about 10%, big difference. So I'll choose not accurate conclusion. As we have C milk to be less than C water, so Q milk will be less than that of water. And from the graph, we have a proportion, or as T increases, Q increases. So T milk less than T water. Okay. We have anti-neutral, so this is beta negative, -1 in the atomic number. So this should be 39, and the 0 mass number, so this should be 90. We have activity equal to minus lambda n, lambda equal to ln2 over t half, so 0.693 over the t half given here. And n will be the activity given divided by lambda that we have just calculated. Okay. This gives the answer of this number of nuclei. So we should first calculate the activity after the time given here. We have a node given before. Okay. And we calculated lambda. And the time is 1000 times the conversion. It's very nice from the examiners to help us with the conversion. You can do this on your calculator, and the result is in second minus 1, this integrations per second or second minus 1 or becquerel. And when you compare this result with the value estimated here, you can find the difference to be very large. Here is 10 to 6, and the value estimated is 10 to 15. Don't, of course, need to find any difference. It is very obvious, unless you are tired like me right now. So it is inaccurate. Hertzsprung-Russell. This cluster is old because no upper part of main sequence. You can see there is a miss part here. Also, we have here the white bar. Okay. To evaluate the accuracy regarding the radius, we have a relation for the radius, which is Stevens-Boltzmann 4 by r squared over a sigma Boltzmann constant t to the power 14 Kelvin to the power 4. We certainly can use this equation, but we have a problem here. We don't have temperature. So as we saw a lot, we will use the Vane's law. Okay. Lambda max here is given as this value. We can substitute after the arrangement, find the t equal to that number. Then you can go up after the arrangement also. R should be L over 4 pi sigma t to power 4 all under square root. Can substitute by the values. These are given above here in the question, or for temperature, you just calculated. 12 gives you this value. Certainly, when you make a ratio to the radius of the sun, it would be 24. Difference between 24 and 25 is almost 4%, so it is accurate. As temperature is greater for Arcturus than Sun, so we will have it to the right, because as we go from left to right, we have temperature decrease. And by the way, here is we should add values and units. We choose unit to be Kelvin and values to start from 60,000 and in 2000. Okay. Again, for Arcturus, temperature is greater, so it should be to if sun is almost say 5,000, so 4,000 should be to the right. So here is say the sun, and here is Arcturus. Okay. Okay. And also, so the sun greater, so Arcturus to right. Also, we have our sun our Arcturus greater than our sun, so we should put Arcturus up. Okay, because we have luminosity increases upward, and relation between L and R is a direct or a proportionality. We have L equals 4 pi R squared sigma T to power 4. Okay, so as radius increases, L increases. As usual, we have here weight downward and loose upthrust, weight downward, and air resistance downward, and upthrust is greater than weight and air resistance, so resultant force upward. So we have here temperature increase. This means increase in kinetic energy, and increase in V or mv, which is the momentum. This means more collision, and the more collision means increase in delta mv, change in momentum. So increase in force, because force equal delta mv over delta t. As force increases, pressure also increases. Okay. Binding energy per nucleon versus nucleon number. explain why uranium 235 releases energy during fission, but helium-4 doesn't. When binding energy increases, this means there is energy released, right? So as uranium 235 make a fission, it decreases in nuclear number and hence its binding energy increases. And as binding energy increases, energy is released. Okay, so this is only for uranium fission, but for helium helium 4 binding energy with nuclear decreases. If you look here, if helium goes to less nuclear number by fission, this means binding energy with nuclear decreases, and as it decreases, there is no energy released. Situation is different for uranium. Fission decreases nuclear number, increases binding energy with nuclear, and hence releases energy. Regular problem where we first calculate mass defect, and here is for neutrons. This all minus that of the nucleus. Okay, gives this number in U, and we have either to convert U to kilogram, and after that use Einstein equation, multiplying the result here by 3 times 10 all squared. Okay, here we will get the answer in Joule divided by 1.6. Okay, and by 10 to the power 6 to get it from Joule to MeV. Okay, this is one approach. Another approach is to use the already calculated 934 MeV for 1U. This is the equivalent energy of 1U. So we can just multiply this number by 934 and we will get the answer in MeV in a shortcut. Okay. However, in the mark scheme, the only way mentioned is this method. Okay. One last thing, don't forget to divide by A in both approaches, and the answer should be 8.53 MeV. Okay. We need the Ba pair A for uranium, and we should use the graph. It is obvious that we have just calculated Ba pair A for iron 56. It was 8.54 MeV, and this is represented here by 1, 2, 3, 4, 4 big squares, and 1, 2, 3. So this is 4.3 for uranium, as we have the value 1, 2, 3, and almost 3.8. So how much is it in MeV? We can make a scissor product where this unknown is equal to 7.55 MeV. You can find a slightly different value here in the mark scheme, 7.44 MeV. I expect because of it is not perhaps it is 3.8, but here is it may be more than 4.3. Okay, anyway, it goes with the same way of solving. So trigonometric parallax is consider the sun here, and the star is here, Earth in this position. Okay, there is an angle theta, and after 6 months in this position there is another angle theta. This is the distance d, and this distance is r, so tan theta equals r over d, and d equal r over tan theta, or theta, as theta is very small. Okay, so we first need to determine the angular displacement of the star over 6 months. Use the trigonometry like this, okay, where r is radius of Earth's orbit around Sun. Okay. White dwarf is very dense, very hot, or high, very high temperature. There is no fusion anymore in white dwarf, and it has low luminosity. So we need to determine luminosity, intensity. And as luminosity is known because they are standard candles, and standard candles are stars with known luminosity. So by determining I, and as we know that I equals L over 4 by D squared, here is the star, here is the Earth, and this is the distance D. So intensity is luminosity divided by 4 by D squared. So from this, D can be measured for the supernova, okay? And if D is known for supernova for any galaxy, the intensity ratio of supernova, and from the relation, is equal to D squared supernova over D squared galaxy. So if we know D for supernova, we can, and we certainly measure this and this, so we can simply get the distance of galaxy. As usual for a geostationary orbit or orbit where it is just above the equator and have a periodic time of 24 hours, we have the potential at this position, the force at this position equal to the centripetal force. Okay, and I choose mr omega squared, not mv squared over r, because we have a period, okay, and it is a simpler than using mv squared over r and then trying to replace v with 2 by r, say, over t or whatever. So we will eliminate m from both sides, rearrange for r by multiplying here. So it is r cube equal g m over omega squared, or it is r equal cubic root of this fraction. Substitute. Here is the mass of Earth, and for omega it is 2 pi divided by the period, which is 24, but it should be converted to second because we have this in SI, this is SI, so this should be in SI. In your calculator, use the fraction, and in the denominator, use another fraction, and the answer will okay. But the question asks not about the distance from center of Earth to the satellite, okay? It asks about just the height, which is this distance, okay? So if all of these distances are, h is equal to r minus this r capital or radius of Earth. So we have here h equal to r minus r of Earth So equal to this value minus radius of Earth is given here. Okay, so the height will be something like that. Okay. Lasers here will do the function of standard candidates.